Hi folks, in this video I want to talk about what is work from a very conceptual point of view. I think other videos do a good job of using the formula in a quantitative way and doing example problems. I want to focus on the concept to sort of build your intuition. So that's going to be the focus of this video, and I want to do it through some examples. So example number one, I have a book, great book, Nonviolent Communication by Marshall Rosenberg. I highly recommend you check it out. This is my system. What are different ways that I can transfer energy to the system? There's a couple of different ways, and there's some just broad categories. So if I have just an isolated system, there's three general categories. Number one, I could heat this thing up. And I want to distinguish between different kinds of heat. So if I place a very hot object on this, the molecules of that object would be colliding with the molecules of my system. That would be heat transfer by conduction. So literally colliding molecules. If I have a hot fluid, let's say the air that's being heated up by this flame, that is transferring heat to this also, kind of like an oven, or like your radiator in your building. That is heat transfer by convection. So there's this class of energy transfer: conduction, convection. That's really the realm of thermodynamics. It's cool. It's not something that we focus on in intro physics. There's also another kind of energy transfer, and we do it all the time. So we can see this flame because it's at a certain temperature, and there is visible light being given off. But if you had an infrared thermometer, you would see that an infrared camera, I am glowing in infrared. If you heat up a metal pan, eventually it's going to start to glow and give off visible light. But there's also kinds of light that we can't see that are just being given off. So this whole category of light, we all call it electromagnetic radiation. That is another form of energy transfer. Think microwaves, ultraviolet, X-rays. These are all kinds of energy transfer by electromagnetic radiation. It's all the same thing. It's all light, just of different wavelengths. There's also other kinds of waves besides light. There's sound. Maybe you've seen a singer crack a wine glass with their voice, and essentially you can transfer energy through waves. So this second class of things, waves and radiation. This is another thing that we're not going to talk about. I just want you to conceptually know that there's other things besides what we're going to talk about in specific physics problems. We actually will talk about waves later in the year, but we won't be using them in energy diagrams typically. Okay, so the main one is work. And let me return to my example. I can transfer energy to the system. Again, the system is just the book. So the only kind of energy this thing can have, if it's just the book, is kinetic energy. So you can ask yourself, how can I give this kinetic energy? Well, I can do one of these two things, or I can exert a force on it. When I exert a force on it, I'm accelerating it, I'm giving it kinetic energy. And that's really what work is. It's energy transfer by an external force. Some words. I'm exerting a force on this right now, but the energy isn't changing. So am I doing work on the book? By the physicist's technical definition, no. There needs to be a sort of a net transfer of energy to the system. The force that I'm exerting upwards on this book is being counteracted by the downward force of gravity. Essentially, the kinetic energy is constant. So if the kinetic energy is constant, no net work is being done on the system. No net energy is being transferred into or out of the system. Let me just pause. Okay, so to summarize, what is work? It is energy transfer by forces external to the system. And there's two key ideas. it's positive when, and it's negative when. So I want to return to this example. When I throw this book up, am I increasing the energy of the system or decreasing the energy of the system? When it starts off at rest and I exert a force on it, accelerating it, then I'm increasing the energy. We say the work is positive. And in this case, when on the way up, when the book is on the way up, you can see that the kinetic energy, it decreases. Why does it decrease? Where is that energy going? There's a force external to the system. The energy is actually leaving the system because of that force. Can you see what that force is? Where is that energy going? Why does it slow down on the way up? It slows down because of gravity. So there's that force that's external, and it is decreasing the kinetic energy. So in that case, that would be an example of negative work. I want to do some examples, but I want to talk equation-wise. So the equation for work, we give it the symbol F. F times, really it's the displacement, delta x, that's what we've seen before, times cosine of theta. What you'll often see in reference tables is that this delta x is replaced with a d, so ft cosine theta. But really this is just the work done by a force is the force times the displacement of the object times the cosine of the theta is the angle between the force and the displacement. So let me illustrate that with an example. Returning to my hand and the book and the gravity. So visualize the free body diagram. You got gravity going down, normal force from my hand going up. If I move like at a constant velocity horizontally, the force that I'm exerting on this is up. The displacement of the object is horizontal. And so the angle between them is 90 degrees. And if you're good with trig, you can realize that cosine of 90 is 0. So in that case, when the force is completely perpendicular to the displacement, it's not adding or subtracting from the energy of the system. It's not doing any work. Now, if I'm pushing in the direction of the motion, in the direction of the displacement, then the force is this way, the displacement is this way, and therefore there will be some work done. Now, if the object is going this way and I push on it, so object is going this way, I push on it, the force is this way, the displacement is this way, the angle between them is 180 degrees, and therefore this would come out as negative. That's kind of how the math works out. If you're more intuitive like I am, I'm thinking, as this thing is coming at me, is the kinetic energy of this increasing, decreasing, or staying the same? And if it's because of me, I'm slowing this thing down, I'm decreasing the energy, the kinetic energy of this, that would be an example of negative work. If I am increasing the kinetic energy of this, I'm doing positive work on this. Just to reiterate the previous example, when I accelerate this upwards and I throw it up, I am increasing the kinetic energy. Therefore, positive work is being done. When this thing is in the air and gravity is slowing it down, it's decreasing the kinetic energy of it. Gravity is doing what we call negative work, leaving that system. On the way down, it's just the opposite. And let's look at that example. Okay, let's look at one example, the example I just talked about. Dropping a ball from a certain height. It starts off at initial 0 velocity. I'm going to say y equals 0 is down here. The snapshot B just before it hits the ground. So this example on the left, I want to focus on what we've just been talking about. If my system is just the ball, and hopefully you can kind of do it in your head without too much trouble, what the LOL diagram would look like if the Earth is in my system. So for now, let's start with this, the ball and the Earth. So if I put the Earth in my system, where does the energy start? gravitational. Starts off at 0 speed, so there's no kinetic energy. And at the end of it, there's no gravitational energy. It's basically at y equals 0. Therefore, it's all kinetic. That is in the case of the Earth in the system. But if the Earth is outside the system, then the ball has no energy to start with. Ek is 0. There is nothing to interact with, so there's no gravitational energy. But in the end, there's still that kinetic energy. We're not changing our choice of system, doesn't change the underlying physics. If it ends up with, let's say, a speed of 5 meters per second, choosing this system, that speed of 5 meters per second is still going to be there. It's going to still have that same kinetic energy. But if the Earth is outside my system, now the energy isn't coming from inside, it's coming from outside. And that is what we represent as work. So this is the work done by the Earth. Just to recall, translating this equation would be the gravitational at A would be equal to the kinetic at B. Here, it's the work done is equal to the kinetic energy. You might want to specify the work done by what force. In this case, it's gravity, or you might not. You can see that these things should match. So in this case, work and gravitational energy, they come out mathematically the same. What is the force being exerted on the ball? It's the force of gravity. What is the displacement? It's that change in height, let's call it h. And what is the angle between the force of gravity and the displacement? It's 0. So cosine of 0 is just 1. So the cool part of physics is you can choose different systems, but your final analysis ultimately should be the same. They should agree with each other. The force of gravity, again, is just mgh. So work is really just another way of looking at what we've already been talking about. If I put a spring outside my system, instead of calling it elastic energy coming from inside, it'd be work done by the spring is equal to whatever the final energy is. That's the key idea with work, and hopefully looking at some quantitative examples and other videos will help clarify that. To summarize, what is work? It is energy transferred by forces external to the system. I can have energy being added to the system. In that case, the work done is positive. I could also have, typically the example would be friction. If I have something with kinetic energy and it's slowing down, then the energy will be leaving the system. We would say the work is done as negative. And actually, let me do that example really quickly. Okay, that example that I just described, a box is moving on a level floor. It starts off with some speed, and at the end of it, it comes to rest. So snapshot A, it has a speed. Snapshot B, it's at rest. I'm going to do this example with two different systems. So in the system that we've kind of looked at before, if the box and the floor are in my system, then this thing has some kinetic energy. And at the end, where did that kinetic energy go? It went into thermal. The bottom edge of the floor heated up. So that would be thermal energy. But in the example of the floor not being in the system, it would be more appropriate to say that the energy left. So again, I start off the same kinetic energy, and at the end, there is no gravitational or thermal because it left the system. I would draw an arrow going out. My equation here would be Ek minus work done by friction is equal to 0. It's minus in this case because the energy is decreasing, it's leaving the system. I can rewrite this as the kinetic energy is equal to work, and in this case, Ek is equal to a thermal. This is typically the way that textbook problems expect you to solve for it. I personally like this approach, and I'll explain why in a later video. Okay, hopefully that was helpful.